So this is the first in two videos explaining how we take in gravitational considerations when we look at our conservation of energy. Remember from first term that conservation of energy sets up kinetic energy plus potential energy plus any work you do on the system equals kinetic final plus potential final. We're not going to write about friction for now. We may talk about it later. The sort of most basic version of this would be if you wanted to find the work to move an object from the surface of the Earth. So there's the Earth, we have an object sitting on it, we want to move that object up to some higher height, and the object's now above the Earth. So to solve that, we would say that the initial potential energy, and it has potential energy because R is not zero, it's at the surface of the Earth, plus the work you do on it is equal to the potential final. So that becomes negative g times mass of the Earth times the mass whatever the object is, divided by the radius of the Earth in this case, plus the work you do on it, the number of joules you add of energy, equals negative g times the mass of the Earth times the mass of the object, all divided by the radius of the Earth plus the height above. The rest of that all becomes just calculator work, but that's your basic setup if you want to lift something off the surface of the Earth at some height above, and you want to calculate how much energy you need to put into the system. A variation of that question would be if you are not doing work, but you're projecting something like a projectile, you're launching it up at some speed, and you want to figure out how fast or how high it travels. So here again, we have the Earth, we have an object sitting at the surface, but this time we launch it with some initial velocity. And of course it rises up to some height, but at the highest point, its velocity is zero. So our equation to set up the second part of this would be that our kinetic initial plus our potential initial would be equal to our potential final. So that's going to be 1/2 mass of the object you're launching times its initial velocity squared plus negative g mass of the Earth times the mass of the object divided by the radius of the Earth, and that's going to equal negative g mass of the Earth times the mass of the object you're launching divided by the radius of the Earth plus the height above. And then remember that if it tells you a height above or altitude, we use radius plus height. If the question tells us a distance from the center, we're going to use just that value to solve these questions. The last sort of variation in terms of just purely energy conservation, and I'll keep our energy conservation line there, would be if you had some object, this is the Earth again, we have some object some distance away, and maybe it's moving with some speed, and it's going to fall back towards the Earth. It's of course going to speed up and hit the Earth with some final velocity. So let's say we wanted to find out what speed it hit the Earth. Here, our conservation equation is almost everything here. We have kinetic initial, we have potential initial, we have kinetic final, and we have potential final. So 1/2 mass of the object, initial velocity squared, plus negative g m of the Earth, mass of the object divided by its initial radius, or how far away it is to start. That's going to equal 1/2 m final velocity squared plus negative g mass of the Earth, mass of the object, over the final radius. And in this setup, we'd be solving for our final velocity. Fairly intensive on your calculator, but conceptually it should be okay to set up.